Hello, kids. Mr. Dorfler here with another round of physics notes. Today, we're going to be talking about projectile motion. And we're going to be taking this section 3 from your book. We're only going to do the first half. And that first half is talking about objects launched horizontally. We're not going to do the objects launched at an angle. That's just a executive decision that I've made. We're only going to do the first half. And what's neat about this concept of projectile motion is we're taking ideas from this chapter where we have to resolve our X and Y components, but then we're going to incorporate stuff that we saw back in the chapter 2 with motion in one dimension and looking at those what they call kinematic equations on how we can solve for velocity, vertical acceleration, any of that stuff, okay? But we're really only going to use 2 of those formulas that we saw in chapter 2. So it's a little combo, if you will. Going to round up this chapter. Again, we're not doing section 4 with chapter 3. I've pretty much always included that section 4 in with chapter 4. And so once we're done with today's discussion, we're going to be done with, quote unquote, this chapter's material. And you can expect a test here in the next couple of days. Your test for this instance will be online. Okay, so you will be taking it at home or wherever you take your tests. But let's begin today because the discussion part's going to be relatively short, but I also do want to go over some examples. And then just remember that you will have a problem bank associated with these notes. In the instructions for the problem bank, I will let you know which problems are going to be crossed out, if any at all, okay? So without further ado, let's get started. So we're going to recognize examples of projectile motion, describe the path of a projectile motion as a parabola. That's pretty much how we described it right there. It's a parabola. And then we're going to resolve vectors into their components and apply kinematic equations to solve problems involving projectile motion. So, objects that are thrown or launched into the air are subject to gravity. These are what we call projectiles. So anytime you toss a ball up in the air, that is considered a projectile. It follows a curved path. Whenever we throw, launch, or projected near the Earth's surface, okay? Now, that curved path is a parabolic trajectory. Okay, that's very important. Why do you think it's highlighted? Okay, very important that you know that it follows a parabolic trajectory. Now, whether or not we put a horizontal aspect to an object's motion or projectile's motion doesn't really affect what's going to happen here, okay? When we have projectile motion is free fall with initial horizontal velocity. So if we look at this image here, the yellow ball is given an initial horizontal velocity, and the red ball is simply just dropped, all from the same height, nearly the same identical location. Okay, they fall at the same rate. In this book, the horizontal velocity of a projectile will be considered constant. But again, we do a lot of this in our lessons here for this book. We don't account for air resistance. So this image, what we see here on the screen, those red and yellow balls, those are most likely in some sort of air chamber, okay, or vacuum chamber that does not allow for air resistance to be affecting their overall rate. But what you see is whether or not you give an initial horizontal velocity, you're still going to have them falling at this same rate. They are nearly identical looking at their positions over certain periods of time. So this is where the kinematic equations come into play. How do we know the displacement, velocity, acceleration of a projectile at any point of time during its flight? Well, what we're going to be doing is we're going to resolve our vectors into components, or your X and Y. Then we're going to go back to chapter 2 and apply simple one-dimensional forms of equations that are going to help us solve for the horizontal and vertical. And then we're going to put them back together. We're going to mush them together into one whole formula. And then we're going to determine our resultant. So to solve projectile problems, we have to apply the kinematic equations in the horizontal and vertical directions. And don't forget, in the vertical direction, that the acceleration, or the AY, what we say the vertical direction, will equal negative g, so a negative 9.81 meters per second squared, because the only vertical component of acceleration is free fall acceleration. In the horizontal direction, the acceleration is 0, so the velocity is constant. So that may not mean anything to you just by reading that, but ultimately those statements right there give us a hand, if you will, in determining what formulas are going to be used. And you can see what formulas are going to be used. They are found in your textbook. I'll rewrite them when we start doing our practice questions, so you can jot those down and add them to your formula sheet. Okay. Again, we are not doing projectiles launched at an angle. We're just not going to do it. Okay. But we are doing the horizontally launched projectiles. And so we have to remember that the initial vertical velocity is 0. We're just going to assume that we're starting from 0 vertically. It's a weird word. And the initial horizontal velocity is the initial velocity in general. Okay. So let's begin by looking at our first question. The Royal Gorge Bridge in Colorado rises 321 meters above the Arkansas River. Suppose you kick a rock because you are so mad at something. I don't know. Maybe you're playing Among Us and you're not the imposter. I don't know. People get mad about that. So you're mad. You kick a rock horizontally off the bridge. The magnitude of the rock's horizontal displacement is 45.0 meters. Find the speed at which the rock was kicked. Okay. So one thing that I'm going to do a lot for these questions is I am just going to get a little artistic. You don't necessarily have to, but I like to. Okay, and let me know. Actually, I don't know how you're going to let me know, but I'm using a new marker today, so I'm hopefully going to be able to write a little cleaner with this. But, so I'm just going to, over here, I'm going to pretend that I'm drawing the bridge. Okay, this is the bridge. Hold on one second. I can't see that light there. Oh, it's dark. Okay, that's a little better. All right, so here's my bridge. This is going to be, okay, and of course, the new marker I have does not work. All righty, let's see if this one works. A little better. Okay, so there's your x component. That's going to be your velocity, your horizontal velocity. And down this way is going to be your acceleration. Okay, so basically from this origin right here is where I'm going to say that the rock was kicked. Okay, and I'm going to draw a very similar trajectory for the rock that we saw with the yellow ball. So all right, so here is the water that the bridge covers, and from the point where the rock was kicked to where it landed was 45.0 meters. Okay, and really I'm just doing this just so I can get an idea of what's occurring. The top of the bridge to the bottom of the water, we know is 321 meters, but since it's going down, we're going to consider that a negative. Okay? So we have kind of all of our images drawn here. Now let's listen to what we know. So we know that the overall vertical distance was negative 321 meters. Okay? We know that the displacement, the horizontal displacement from where the rock was kicked to where it landed was 45.0 meters. We already know what the vertical acceleration is, negative 9.81 meters per second squared. What we don't know is the speed at which the rock was kicked, right? Okay, so first thing is, let's take a look at what formulas we are going to use. Okay, now listen carefully. Because air resistance is going to be neglected, the rock's horizontal velocity remains constant. So we can use the equation when we talk about horizontal. We can use the equation that discusses, or that has in it, displacement in the horizontal, the velocity in the horizontal, as well as time. You're going to see why we're going to use time here in just a second. So our first formula that we're going to use and manipulate is delta x is equal to Vx delta t. Okay? So that's our horizontal component. Our vertical component, because there's no initial vertical velocity, here's what equation we're going to use. Since we're dealing with vertical, it's delta y. And really, we don't know a whole lot, okay? We know what the acceleration in the y direction is going to be. And we can utilize this time one again, okay? Now, if you go back and read the question, there is no mention of time whatsoever. But what that does is it ties in both the x and the y components. Both formulas for the x and the y have a time component. Okay? So, since they both have that time component, we can rearrange these equations so that they both equal t. And so we can then substitute in. Okay. So, let's just say, okay, for y, okay? For the y part, we basically know this, okay? We know what this will be. So we need to rearrange this equation to solve for delta t so we can then substitute it in a little later. And so what we're going to have is we're going to have a formula that's going to look like this. Delta t is equal to the square root of 2 delta y divided by the acceleration in the y direction. So this is kind of like our version that we're going to kind of use as our stepping stone here. Okay, so we got another one. Okay, we got to rearrange this. To rearrange this to solve for t, we are going to have t is equal to delta x over Vx. Okay? So, basically, what this means is that since these both equal delta t, we can have delta x divided by Vx equal to 2 delta y over ay. So, finally, we have a working formula that both incorporates the x and y direction. All right, so let's get this set up to solve for Vx, okay? So what do we need to do? Well, we need to rearrange this equation to solve for Vx. So once you have done your little bit of algebraic manipulation, multiply both sides by Vx, divide by the inverse of this, you'll get the formula Vx is equal to square root of ay. Notice how this is now flipped from before because of how we had to manipulate it, to delta y times delta x. Okay? Once I have everything kind of situated here, we're going to solve for Vx and just plug in our values. Negative 9.81 meters per second squared divided by 2 times negative 321 meters. Don't forget, that's what the overall height of the bridge was, multiplied by our displacement in the x direction, 45.0 meters. If you want to pause the video right now so that you can solve this on your own, go ahead. But once we have plugged everything into our calculator, we should have an answer of 5.56 meters per second. Okay? Let's do a few practice problems. But before we do, just a reminder. We took their x and y components, okay, took our x and y kinematic equations, set them both equal to t so we could substitute. We then, once we did that, we set both of them equal to each other and solved for our unknown. Since we solved for Vx in this situation, we had to multiply Vx on both sides and then essentially divide or multiply, whatever you want to do, and take the inverse of this, and then that's how your setup's going to be. Now, you're not always going to be setting up and solving for Vx. Let's take a look on page 99 in your textbook. Okay? Page 99 in your textbook. Let's look at number 2. Number 2 says a cat, let me get this here. A cat chases a mouse across a 1.0 meter high table. The mouse steps out of the way, and the cat slides off the table and strikes the floor 2.2 miles from the edge of the table. When the cat slid off the table, what was its speed? So again, we are going to be having another problem or another situation that we need to solve for Vx, okay? So again, let's look at just the image here of what's going on, because I like to draw pictures, apparently. So again, here's the table, okay? Here's the ground. The cat, here's the edge of the table right here at the origin. The cat lands right here. Okay, here's the kitty cat. Kitty cat, big tail. All right, from where it slipped off the table to where it landed was 2.2 meters. Okay, the height of the table is 1.0 meters, but again, it's going to be negative because it's in the vertical direction. And so what do we know? We know that, again, delta y is equal to negative 1.0 meters. Delta x is equal to 2.2 meters. And again, our ay is equal to negative 9.81 meters per second squared. Okay? So again, since we're solving for speed, Vx is going to be equal to square root of ay over 2 delta y multiplied by delta x. Plugging in our values here for, again, ay, negative 9.81 meters per second squared divided by 2 times negative 1.0 meters, and multiplied by delta x, which is 2.2 meters. So again, if you want to pause your video and solve this on your own, go right ahead. Here in the next few seconds, I will go ahead and give you the answer. So once you have solved or plugged all this into your calculator, you should get an answer of 4.9 meters per second. Excuse me. Let's look at a different scenario now. All right. Let's look at number 4. Okay. Well, first of all, number 4 is built off of number 3. So let's read number 3 first, okay? Okay. So number 3 says a pelican flying along a horizontal path drops a fish from a height of 5.4 meters. The fish travels 8.0 meters horizontally before it hits the water below. What is the pelican's speed? So before we go, if you solve for number 3, if you go ahead and practice number 3 in here, you should have an answer of 7.6 meters per second. Now, the reason why I say that is because we have to use that number in number 4. Okay, so let's look at number 4 now. If the pelican in item 3, which we just read, was traveling at the same speed but was only 2.7 meters above the water, how far would the fish travel horizontally before hitting the water below? All right, so what do we know here? First of all, again, drawing our kind of our situation, what's happening. There's water, okay? So here, we got a fish that hits the water, okay? But we don't know, okay? We don't know how far the fish will land from when it's released, okay? We do know that the pelican was at a height above the water of 2.7 meters, okay? And we do know that the AY, again, was negative 9.81 meters per second squared. We know that, like I said, the speed from tagging along the speed of the item in number 3. So the Vx is equal to 7.6 meters per second. And again, the delta y is equal to negative 2.7 meters. So again, taking the initial equation, okay, where we had, oops, dropped it. Dropped my marker, hold on. All right, delta x equals Vx divided by, or equal to 2 delta y over ay. This time we're solving for delta x. Okay, so all I have to really do is just multiply both sides by Vx, and we're good to go. So delta x is equal to square root of 2 delta y over ay multiplied by Vx. So I can simply plug in our values here. So square root and 2 times our negative 2.7 meters divided by negative 9.81 meters per second squared multiplied by Vx, which is 7.6 meters per second. All right. Again, if you want to pause the video, work it out on your own, you may do so. But I'm going to go ahead and solve this. Should be 5.6 meters. All right, so really the only other variable that you might need to solve for would be the vertical displacement. Okay, and you just follow the similar rules that you would anytime you have to rearrange anything. Okay, so a little rusty in the videos this morning. Things just weren't cooperating a little bit with me. So if you have any questions regarding your homework, just hit me up with an email. But other than that, be studying for your exam. Get your homework completed and pay attention to due dates. And I will see you all later.